objects, and especially we don't know if they are identical to their antiparticles or not. Neutrino is equal to an anti-neutrino or is the same particle. And the most promising way to give an answer to this kind of questions is to look for neutrinoless double beta decay. This is a nuclear decay, so it's, you need a heavy nucleus that should be converted spontaneously into an isobar emitting 2 electrons or positrons with or without the emissions of these neutrinos. And in this process, the nuclear charge changes of 2 units while the mass number remains the same. So if you look in the Segre chart, this is a zoomed vision of the Segre chart, the double beta decay makes a double jump in this diagonal direction. So you, for example, start from germanium-76 and you end up in a selenium-76 with this jump. And this process is, of course, mediated by the weak interaction and is observable in even nuclei where single beta decay is energetically forbidden. Let's make the example of A = 76 isobar chain. You start, for example, from one of these isobars. These are unstable against the single beta decay, and you end up to, for example, germanium-76, but this cannot decay anymore due to energy conservation to arsenic-76, but still there is the possibility of a double beta decay. So as I said, there are 2 versions of this decay. One was predicted by Maria Geppert-Mayer in 1935, but this is just a second-order version of single beta decay, so it's just an exotic process. Actually, it's the process among the observed ones with the longest half-life ever measured. But it's completely within the standard model, so there's not very much to say about that. But there is a version, which is this of neutrinoless case, where, which is only possible if a neutrino is emitted by a neutrons and absorbed by another neutrons, which is only possible if neutrino and antineutrino is the same particle, as predicted by Ettore Majorana in 1937. And the process was introduced by Farry in 1939 as the smoking gun of the fact that neutrino is equivalent to the antineutrino. So this process has never been observed, and this is very important to study for possible events of this process, because it's completely beyond the standard model, could demonstrate violation on the lepton number conservations, and will give us access to the neutrino effective mass, and also other important, let's say, physics beyond the standard model, like CP violation in lepton sector, and also a way to leptogenesis and grand unification theories of fundamental interactions, and so on and so forth. But here you can see that if this process will be measured one day, the half-life of this process does not give us the information about this object here, which is the piece of physics beyond the standard model, because you need to know the matrix element, the nuclear matrix element, which is this quantity here. This G factor is just a phase space factor that can be very accurately calculated, so it's not a problem at all. So let's focus on the nuclear matrix element. The nuclear, these are here represented in a symbolic way. You have a nuclear state here, an operator here, weak interaction operator, second order one, and another nuclear state here. So this quantity here is a mathematical quantity, it's not a physical observable. Cross-sections are observable, decay rates are observable, not the matrix elements. But, and can be only established by calculations. But although much work has been done on the operator, on the transition operator, now incorporating all the known physics of the weak interaction, the real problem is in the nuclear states, because nuclear states are many body states. Many body states means very complex objects, and that is the problem. And just to show that that is the problem, I will show you a very recent review of modern physics published last year, where the authors collect all the known calculations, state-of-art calculations with all the best, let's say, state-of-art theories, QRPA, large-scale shell model, IBM, ADF, and so on, also ab initio. But you see that for each isotope of interest, still there are big tensions. So I should say that this figure, you can see the same figure in the last 20 or 30 years. So there has been not so much progress here. There was a progress, but still we are very far from being, let's say, in a good condition. So theory, but also experiments, because to make good constraints of these nuclear matrix elements, we need a lot of data, because these theories must be constrained with data. And this is what happened. And there are different sources of measurements that still are not yet enough to constrain the matrix elements. I group here in first order isospin and second order isospin probes. You have a plethora of these things. Here, beta decay, 2 double beta, pi plus, pi minus, single charge exchange, and so on, transfer reactions, and so on and so forth. But my focus today is on heavy ion double charge exchange processes, which has been introduced a few years ago as a tool to explore this kind of physics. So I say the new experimental tool, not so new, because now it's about 10 years that we talk about that. But what is the concept? The concept is that heavy ion-induced double charge exchange reactions could be surrogate processes that stimulate in the lab the same transition that spontaneously occur in a nucleus when there is a double beta decay. So here, this is the question. You have to wait a long time for a double beta decay. Here you stimulate in the lab the same nuclear transition. And you can see that represented in this cartoon here. This is the double beta decay that connects, for example, germanium-76 to selenium-76. But you can promote the same nuclear transition by an heavy ion reaction, like neon-20, oxygen-20, for example. With the reaction, you can, of course, make the inverse. You can start from the selenium-76 and make oxygen-18, neon-18, and go to selenium-76. The nuclear matrix element must be the same for time invariance. But, of course, when you do this, a lot of other competing reactions occur in the same collision. And this is more or less what happens when you do a reaction, nuclear reaction with heavy ions. And there are a lot of processes that subtract cross-section to the channel of interest, which is double charge exchange. Not only, and some of these could end up to the same nuclear state, which is fed by the double diagonal transition you are interested in. So I talked about surrogate process. When you have a surrogate, you need to understand what is the difference and what are the similarities. The differences are quite clear. I mean, in one case, you have a strong interaction in double charge exchange reactions. In the other case, you have a weak interaction working. There is another big difference. One is a decay, and the other is a reaction. So the dynamics is different. And also, double charge exchange includes sequential transfer of nucleons, which is, of course, not possible in a double beta decay. So these are big differences. But there are important similarities. For example, you end up to you connect the same initial and final states, not the models as in the theories. Here you have the real states. And the operators are different, but from the mathematical point of view are not so different, because you have in both cases short-range interactions, short-range operators with a cocktail of Fermi, Gamow-Teller, and tensor, although the weights are different. But in the double charge exchange, this cocktail changes as a function of the bombarding energy, so you can tune the three components of the operator, making the experiments at different incident energies, for example. And another crucial similarity is that both processes require a large linear momentum available in during the process itself. And this is a fundamental similarity. Both processes are non-local. They are localized in a pair of nucleons. They occur in the same nuclear medium, so you can explore, for example, quenching phenomena and things like that. And in both cases, you have a big off-shell propagation. So, as I say, double charge exchange mechanism is a complicated reaction mechanism. Could proceed either directly, like this, is one step. This we call Majorana double charge exchange mechanism, which rely on short-range and nucleon-nucleon correlations, leading to the exchange of a correlated pair of mesons. And this has been discussed along by Professor Lenske in this very recent article of 2 weeks ago, let's say, where you can find a detailed description of this process. But you can also have a double step, double single charge exchange, where you have two consecutive single charge exchange processes which are not correlated each other. And these rely on nucleon-nucleon isovector interaction. And again, there is a very recent paper from Lenske 1 month ago, 2 months ago, where you can find the details of this theory. But you can also have this high order mechanism where you exchange nucleons, at least of 4th order, which are mediated by the mean field. And of course, the double charge exchange cross-section is a combination of these three mechanisms, and you have to sum them coherently. So that's the complication. So it's fine recent literature about that. And the Newman collaboration is very committed to study this kind of phenomenology in the way that I outlined just before. The double charge exchange program has started at INFN LNS in Catania. Here is Catania, it's in Sicily. And Catania was founded also by Greeks, and I should say maybe a few years before now in Naples. So, so we, yeah, we have to investigate who was the first. Yeah. And we have a laboratory here, and we have 2 accelerators. One is a superconducting cyclotron, which is let's say, the accelerator used for this kind of research. And you have a large acceptance magnetic spectrometer called MAGNEX, which has a quadrupole and dipole. I don't talk about that, but just to say that this object allows to have a large solid angle, large momentum bight, and also providing quite good energy, angle, and mass resolution, and also works in a quite large dynamic range. And Professor Soliotis allowed us to explore how large is this range with experiments measuring zinc isotopes and things like that. So the multi-channel approach is the big part of my, but just to say something. So as I said, when you have a collision, you are very much interested to a reaction channel, but you have to pay the fact that many other reaction channels occur and are much more likely to occur than the one that you are interested in. So these are bad things. I mean, you call typically background, these kind of things, and you have to fight very hard to try to disentangle your signals from all of these background. But apart the negative aspects, there is positive aspects in this, because many of these reaction channels are quasi-elastic. And the quasi-elastic reaction channels are quite important because they are very selective of very specific degrees of freedom. So you can use all of these to learn much more about the many body states which are, let's say, at the origin of the uncertainties in neutrinoless double beta decay matrix element. So, although the main interest is in double charge exchange, let's say we can explore all of these and build a constrained analysis of nuclear states. For example, we study elastic scattering, we get nucleus optical potential. In elastic scattering, we get knowledge about coupling strength to low-lying states, and so on and so forth. So this is our vision. If we measure all of these channels at the same time, under the same experimental conditions, we get a high reliability of the measured observables because we can make a lot of cross-check in the data. And from the theoretical side, if we analyze all the data in the same way, we can reduce the need of free parameters in both nuclear structure and nuclear reaction, let's say, models. So this is the idea. And we, let's say, already use these in a series of nuclear of interest for neutrinoless double beta decay, cadmium, germanium, and isotopes, and so on. And these are some literature about that we have recently produced. But we also explored other systems which are relevant for the reaction mechanism, like calcium-40 or carbon-12. And just a feeling how it works, let's consider this case of calcium-40 and oxygen-18 plus calcium-40 at 270 MeV case. This is just a case to demonstrate how the multi-channel approach works. So we first measure elastic and inelastic scattering. We get a spectrum with the magnetic spectrometer. We build cross-section differential angular distributions. And we analyze this, for example, in quantum mechanical approaches like coupled channel calculations using, for example, double folding potentials. For example, the San Paolo one, but we could use whatever we want. And we found that the coupling to low-lying 2+ and 3- collective states are very important for that. For example, effects of coupling can be accounted for in the initial and final state interaction by coupled channel equivalent potentials, but this is technicalities. But once we do elastic scattering, we analyze transfer. For example, this is one proton transfer. This is for the target and the projectile, which occur the opposite transition. We again get the spectrum. We get the cross-section angular distribution. Here, the optical potential is frozen. It's the same that we fixed by elastic and inelastic scattering analysis. And we have to use a model for the, let's say, for the transition. And we use large-scale shell model. We have a large model space and state-of-art interactions, for example, this one. And what we learn that we can describe very well in quantum mechanical coupled channel Born approximation theory the data. Is a typical example. And we understand that the mixing of single particle and let's say core polarization configuration is important in these, let's say, reactions. Then we move to one neutron transfer and we do the same exercise. Again, the optical potential is frozen. Also the shell model interaction, the model space is frozen. I mean, everything is frozen. And we just apply this to one neutron transfer and we get very good results with the same conclusions that the best is from coupled channel Born approximation, so quantum mechanical theory for reaction. And again, we get that the mixing of single particle core polarization configurations are quite important. Then we move to two nucleon transfer. For example, two proton transfer is the same. Now everything is frozen. There is no other to be added. And the cross-sections are very low. And again, we have to compare one-step double jump with the two-step mechanism. We do that. It's a big calculations. Everything becomes more complicated, but the ingredients are the same. And we get very good results again here without any change of anything. So all the data are analyzed in the same way. Then we move to charge exchange. For example, you can have charge exchange like this, so driven by multinucleon transfer, for example. And everything now is frozen. I don't need to talk about how we do the calculations, how the same calculations done in the same way. And we get, you see, that for the ground state region, we get good description of cross-section. Then the calculation starts to be lower than the data. So it means that there is something else in the real data that is not just transfer. And this is what we call the meson, sorry, it's not working anymore. What we call meson exchange. This is the diagonal part. And we do that in QRPA and recently in shell model. We run the calculation and we see the opposite. You see that the ground state is depleted and then the more excitation energy we add, the better results we get. So just, I mean, of course, to do single charge exchange, you need to do this and this all together. This has never been, it was done only in the 90s, now it's 30 years. It's like in the moon. I mean, people went in the moon in 1969 and nobody was able to go back there. The same is true here. People did, only one calculation exists in 1990 and nobody was able to do that again. So this is, even the people that did the calculation in the 90s, I mean, should. So now we did this. This is the example of carbon-12. This is the second time in the history that such a big calculation is performed. And show the case of carbon-12. Now we are applying to calcium-40. And then we move to double charge exchange. Again, we do the spectrum, the angular distributions. You see here. The cross-section are extremely low, as you can see. And as I say, there are three reaction mechanisms. And we did a very big calculation with the multinucleon transfer with all the parameters frozen, as I said. And we cannot, let's say, reproduce the cross-section, meaning that the multinucleon transfer is not the mechanism. So we have to think about meson exchange, pion exchange especially. And we have the two mechanisms, the Majorana and the double sequential one. And these are the results that have been recently published in the two articles that I showed you before. And of course, this is the last slide. Only a few systems have been studied in the present condition, but the reason is that the cross-section is very, very low, and we need a major upgrade of the beam current in our accelerator to perform this. If we want to systematic study of all the cases of interest. And that is the reason why we have a big project in Catania called POT-LNS to increase our, let's say, beam power from 100 watt to about 10 kilowatt. It's a big jump, which requires a lot of new technologies, and no time to talk about that, but technologies on the, let's say, cyclotron extraction technology, and also on the target, on the detectors, everything is different. And go to the conclusion, I would like to say that second-order isospin excitation of nuclei could bring a gap between nuclear physics and the neutrino physics. I should say that in the 50s, the two disciplines were the same. Then they bifurcated, and I think that this kind of thing is nuclear physics, which could be useful for neutrino physics. Heavy ion double charge exchange reactions could contribute to this research field because they allow to test the matrix elements. And the multi-channel reaction approach is mandatory in my opinion, and should be general
Also in very recent electron scattering data with very small error bars and so on, published last year by Kegel et al. These data are the open circles here, and still the big difference between the ab initio calculations based on chiral effective field theories and all available electron scattering experimental data, there is a big difference among them. On the other hand, the mystery continues with some news, some very new calculations with a similar model by Meissner and also similar by Hiyama Kamimura, but this calculation seems closer to the experimental data. So, in general, we can say that the calculation of the isoscalar monopole form factor remains an open subject. Continue with the P6 case of this resonance. Let me say that this resonance lies just above the proton separation threshold. So you can see here the resonance centroid according to different measurements. We have also differences on different probes and so on. And here are the obtained widths. Also here we can see that there are differences between the different measurements. And we can see that this resonance is just above the proton separation threshold, but below the neutron separation threshold. So we are in continuum, let's say. Also here we have the open question, what about the line shape of this zero plus resonance? If there are any dependencies on the measurements based on different probes, and also what about interference phenomena? So, to conclude this introduction, let me say that it is important to investigate in general the properties of this zero plus resonance wave function. So, in electron scattering studies, the calculations select only the isoscalar monopole form factor, while we may have also iso-vector components and higher multipolarities in the experimental spectrum. So, our proposal is to study in an exclusive measurement the helium-4 plus helium-4 in elastic scattering, and in this way we expect to have a low background from physics, low physical backgrounds, but it offers also an interesting complementarity with the obtained electron scattering data, some of them very recently. And also, of course, to revisit the existing data sets in a consistent way. About the experimental setup, the experiment was carried out at the Magnex facility in Catania, and the experimental setup was consisted by the Magnex magnetic spectrometer and also a silicon telescope, OSCAR, mounted in the scattering chambers. So the beam was a helium-4 beam delivered by the cyclotron accelerator of the laboratory, impinging the helium-4 target implanted on aluminum foil. So the strategy of our measurement is to measure the helium-4 ejectiles from elastic scattering at Magnex, and also for the case of inelastic and breakup, to measure helium-4 at Magnex in coincidence with a lighter product, so tritium and helium-3 on the silicon telescope. In this way, we have for the first time an exclusive measurement into this direction that ensure an almost background-free measurement. Here, the particle identification procedure, since it can be found also elsewhere, I will not say too much about that, but I want only to point that we have an unambiguous particle identification. And of course, the goal of our study is to clarify previous inconsistencies between different set of data, to extract the characteristic of the first excited state, the 0 plus excited state of helium-4 in a new measurement with a good accuracy, but also to investigate the role of the accessible partial waves. Another point is to investigate some possible interference between the 0 plus resonance with underlying non-resonant S-wave continuum. All of them, we can do the job with a line shape analysis based also on the Fano theory. And last but not least, we have to probe ab initio theories already adopted for the description of electron scattering data. So we have to do that in a new set of data of helium-4 plus helium-4. And in this way, we aim to put some strong constraints towards the solution of this interesting puzzle. So I mentioned for the line shape analysis the Fano theory. So this was introduced by Ugo Fano at 1961 with many applications in different aspects of science. And of course, in nuclear physics, we can see here that with the help of the Fano function, we had a nice reproduction, a nice description of the resonance of lithium-10. Also, this resonance lies very close to the threshold, to the breakup threshold. Also, in our case, we have a resonance very close to the threshold. So here is the line shape analysis with our data, and we can see with the black line the Fano function accounting for the resonant, the 0 plus resonant, but also the non-resonant continuum and the possible interference between them, and also the transfer and the tail of the P-wave resonance, the 1 minus resonance at 24 MeV, which is a very broad resonance. So we can see that we have a perfect, an excellent reproduction of our data, while this plateau indicates a sizable interference with the non-resonant continuum. Here, just for reason of completeness, I present also the results for the mode of which the helium-4 breaks on helium-3 and neutron. Of course, the resonance, the 0 plus resonance, which is the main focus of this work, it's below the neutron separation threshold, and of course we cannot see in this spectrum. This spectrum is dominated mainly by the 1 minus resonance at 24.25 MeV. So let's go now to some cross-section data, angular distribution. The focus is on an elastic scattering. I present also a phase shift analysis on our elastic scattering data in a broad range. But let's focus on elastic scattering. With the two bands, I present the two groups of ab initio theories. The one with the blue, it's the ab initio theory is based on chiral effective field theory, so the theories that solve exactly the problem, but also some other theories that shares among them some similarity based on lattice effective field theories, and so on. And we can see that at least the strength of our data within the errors or within the uncertainties of these ab initio theories can be reproduced by these theories. Let me remind that this theory failed to reproduce the electron scattering data, the form factor of shown in the second slide. And just for reason of completeness, I will show also the situation in the only available set of data in the literature in another energy at 64 MeV. Also, here the conclusion is the same. Going to our summary, So elastic and elastic scattering measurements were performed at the magnet facility for the helium-4 plus helium-4 system at 53 MeV, energy, incident energy, while the line shape analysis by using also the Fano function indicates sizable interference between the resonant and the non-resonant continuum, while the experimental cross-sections were interpreted in the coupled channel framework, adopting physical models from ab initio theories, physical models already used for the description of electron scattering data. And here the indication is that the chiral effective field theory model seems to be in a better agreement with the strength of our helium-4 plus helium-4 inelastic scattering data. Here it's our collaboration, and thank you very much for your attention.
Questions for Vasilis? Yes. Me? In the chiral effective calculations, up to which order do you go? Next to next?
Excuse me?
In the chiral effective theory calculations, up to which order?
Yeah. Here.
Because they have next to leading order, next to next.
Yeah. It's written also in the first next to next to next.
Oh, okay.
So it's the other one. I don't know where it is. It's here. Okay. So, yeah. It's the red one.
The red,
N3LO.
Yeah.
3N, okay. Thank you.
Yes, can you go back to the slide later on where you show the agreement between the
The angular
helium-4 plus
distribution?
yes, showing the
How
what was
we
it?
obtain,
The chiral effective field theory agreement.
So
Keep going. There, that one.
we took from the ab initio calculations
Yes.
the densities for the ground state, for the excited state. In a double folding model, we obtain the angular distribution, also the transition density,
Sure.
all of them from the chiral effective field theory for the case of the blue. So for the case of blue, this band was defined by two different chiral
Sure.
effective field theories calculation.
That is one of my concerns, the fact that the band is so wide and you are displaying it on a log scale.
Yes.
The second concern I have is that your data seem to indicate that there is a dip at around 20 degrees, which is not reflected in the chiral calculations.
Yes, and also that's the reason I mentioned that the chiral effective field theory can predict the strength of the data. Not we can see that we have a clear minimum on the data, and of course the contribution of different partial waves may contribute on that. But let me say that here we have a calculation that is the strength is close to the data. On the other hand, on electron scattering, we see that the ab initio calculations are far away from the data.
Well, therein lies another problem, because trying to describe an isoscalar monopole transition with electron scattering is fraught with difficulty at the best of times. I know that from experience. So I'm not entirely surprised that that was the case with the electron scattering data.
Yes. Okay, but okay, what we try to do is to with a new set of data. So for the electron scattering, we have the set of the experimental data. Now we have with a very small error bars and so on. We have the calculation of the monopole transition form factor, and we have the discrepancy. How to give a new input to this direction? So we have a new set of data. Also, I can show something else regarding the uncertainties, that in order to have under control also all the possible types, let's say, of uncertainty, because these larger, large uncertainty bands that I shown was only the uncertainty band on the nuclear structure input, let's say, on the ab initio calculations. There are also the uncertainties coming from the reaction modeling, but these are shown here and are much less than the ones from nuclear structure input. Still, in nuclear structure input, the bands are quite large.
Neutron-stars. Okay. Yeah, this is just the outline of my talk, a short introduction about neutron stars and with respect to the Hyperon puzzle. Then I will say something about our model that we use. This will be very important, which we apply to nuclear matter. Then, of course, for better equilibrated matter for neutron star relevant densities. Then I have here a section on strangeness threshold effects. This is actually the most important part of the talk. And with this, I hope we will be able to understand these new results that I will show you at the end of my talk. Yeah, let's go to the introduction. Well, neutron stars are actually giant nuclei. These are very important objects, so unique cosmic objects, because they contain contain baryons at high densities, at high isospin asymmetries, so this extreme region which we would like to understand better. On the other hand, they are very stable objects over very long time scales, so we can see them. And also, there are precise data for, at least for the masses of these neutron stars, and some estimations for the radii. So from all this here, you can understand, maybe you can explore better the equation of state under these extremes, high densities, high isospin asymmetries, beyond experiments here on Earth, like collisions between nuclei at high relativistic energies. So some small, short indication about these measurements, astrophysical measurements. So we know there are neutron stars with very large masses, above 2 times solar mass. So that means that the equation of state at these high densities should be very stiff. But on the other hand, we know from terrestrial experiments, heavy-ion collisions, also at high densities, but not so high as those inside the neutron star, that the equation of state is soft. So there is a very, how to say, non-trivial density dependence of this equation of state. This can be, how to say, produced, this non-trivial density dependence by state-of-the-art models. In principle, I mean, this can be done, but here there is a problem. And the problem is the following. So we have here very high densities. So the baryons, let's say nucleons inside the star, have very high momenta from 0 up to the high Fermi momentum. That means that baryons heavier than a neutron can be produced. So they are energetically allowed to get produced. That means that this composition of a neutron star can contain protons, neutrons, leptons, and also hyperons in beta equilibrium. So why is this a problem? This is written here. So when one includes in such a matter more degrees of freedoms than proton and neutron, then the equation of state at these high densities gets softened. So it softens a lot when these strangest particles, baryons, are present in this high density environment. So less, we have less baryon energy available, so that means less gravitational pressure just to keep the star in equilibrium. And so with this, we get a reduction of the neutron star masses in the presence of these hyperons. And this is the so-called hyperon puzzle, because the observed high neutron star masses cannot be reproduced by state-of-the-art models. So that means very successfully models which have been applied to many different nuclear systems, like finite nuclei, hadron-induced reactions, heavy ion collisions, at different energies. They have been very successful, but if we put into these models hyperons and try to explain neutron stars, then there's a problem. The mass gets suppressed because of this effect here. And this is the so-called hyperon puzzle. Actually, this is a very persisting, non-trivial issue over many decades. And one of the reasons, because of this persistence, so to say, is that the hyperon densities in this neutron star environment are very different from the rest, so from the other medium. So that means the momentum of these strangeness particles are different from the rest. So that means that not only the density, but also the momentum dependence of the potential of these hyperons can be, so it's maybe important. So we have here momentum in medium, density and momentum dependent hyperon potentials, which one should in principle take into account. Another problem here comes from the experiment. We don't know so much about hyperons from experiments. So we have some single lambda and one double lambda hypernuclei, so from experiment. Low energy lambda and sigma minus nucleon free scattering, so not in medium. Of course, one can learn a lot from heavy ion collisions. There are a lot of collective flow data, particle production of lambdas and sigmas. But here the problem is the scattering. One should somehow separate different things, which complicates. It's a complicated issue in this reaction dynamics at high energies. And also the other exotics here, Xi, so there's double strains, omega has 3 strangeness. These are still unexplored, so far as I know. So we need in medium density and momentum dependence of the hyperons potentials. As I told you, there are no data, or not so many data in order to compare our models. And so we have to rely on models to see what happens in this high density environment in neutron stars. So the model that I will use here is this nonlinear derivative approach. I will go very fast through these slides. So it's based actually on this famous quantum hadrodynamics. So this is a relativistic mean fielding principle. We use the same Lagrangians from the degrees of freedoms, baryons, mesons, for the interaction. Baryons are the proton, neutrons, lambda and sigma particles. For the interaction, we take sigma, the basic meson, sigma, omega, and rho meson. So the interaction here is what you see in black is the conventional, so standard quantum hadrodynamics, and the blue is the new, which is related to this NLD model here. We inserted here derivative operators in order to get, in a natural way, at the end, so to say, of the day, not only density, but also momentum-dependent fields. So all this, of course, complicates this field theoretical formalism. One gets different form of the Euler-Lagrange equations, energy momentum tensor from Noether theorem, and so on, but it can be done. And finally, one have here a fully covariant, and also this is important. We have checked this many times, thermodynamically consistent approach, which will give us density and explicitly momentum-dependent fields. Yeah, just to show you the relevant equations which one has to use to solve problems in beta equilibrium. So we have the meson field equations in the relativistic mean field approximations for the mesons. Just here, I show you as an example for the scalar sigma and the vector omega meson. Black is conventional equations. The blue parts here, these D's are these functions which are coming particularly from our model, the NLD model. So these are momentum-dependent regulators for each baryon-meson interaction. We call them regulators because they indeed regulate the high momentum tail of all these fields. Finally, we have, of course, in medium Dirac equations, so quasi-free Dirac equations for all the baryons. Again, as in the conventional relativistic mean field theory, but with the difference here that these fields, scalar and vector, are explicitly momentum dependent for all the baryons. So effective mass is momentum dependent. And again, here with these NLD regulators, which we use a generic monopole-like form of this type here. Here we have, of course, these are parameters of this model, cutoffs. We call them cutoffs because they cut momentum-dependent divergences at high momenta. So just some basic features of this model before I will discuss the strangeness effects. So these regulators show up in two ways, implicitly in the source terms of the meson field equations, and explicitly in the baryon self-energies, and all this, and these two lines, so to say, induces a non-trivial density and momentum dependence of all the baryon potentials. So this means that we have a non-trivial dependence of the equation of state, and most importantly, a non-trivial momentum dependence of the single particle energy of each baryon. This is very important for the Strangeness threshold effects. This slide here will be very fast. It's actually nothing, new, no new formalism. We just solve this model for matter in beta equilibrium. One has to take charge neutrality, baryon conservation, and beta equilibrium. So at the end of the day, one has to solve this beta equilibrium equation for this baryon with a solution of this P, so the momentum of the baryon at the Fermi level. The blue is here important because now you see that the fields are momentum dependent, so this will induce new effects, new threshold effects on the particles heavier than neutrons, than the neutron, that is the hyperons. And just show you this conventional threshold effects, which were published many years ago by Glendening. So if you don't have momentum-dependent fields, so S and V just run numbers that depend only on a density which put you as input, this in-medium energy increases monotonically always with momentum. So from this you get only two cases. This is this threshold condition here. If this is satisfied, then you can produce the hyperon. If not, it cannot be populated. And just here two examples, just to demonstrate this effect. Here you see the in-medium energy of a hyperon versus its momentum. This line is the threshold. So if the lowest energy of the hyperon is below the threshold, it can be produced. This will be here the solution. If not, no. So if the lowest energy of the hyperon is above the threshold, it can be produced. So there is no solution. Now, when we include explicitly momentum-dependent fields, all this situation will change, can change, because of these explicitly momentum-dependent fields. So that means that this energy is not necessarily increasing function in P. This is the most important thing here. And just to demonstrate this, in these two figures here, so you see a similar figure as before, but now within this NLD model, even when the threshold is satisfied at zero momentum, the hyperon cannot be produced. So the fields are very soft at high momenta. So in-medium energy is very soft, and there is a solution, but the density is beyond the total baryon density, and because you have baryon density conservation, so this region here, the yellow one, is forbidden, the hyperon cannot be produced. This is one example. Second example here, more in which you have a very, very decreasing fields in momentum. Even if the threshold is satisfied, you cannot produce the hyperon. Of course, there are some strange effects which we have to understand. I don't want to go here into details because of time limitation. And just to show you the results, let me go here. So here on the right, you have a conventional RMF model, this NL row parameterization. On the right, the particle fractions in neutron stars versus the baryon density. And on the left, you have the hyperon fractions, so for lambda, for this NLD model. And you see that can be produced in a very narrow region. So they produce the high densities, and then they disappear again. This is because of these explicitly momentum-dependent fields. This induces a very strong effect here that the equation of state, so if you look at this figure, this is pressure versus energy density, without and with hyperons does not change its stiffness. So this is very important because even if we include all hyperons, so single strange hyperons, lambda and all this strigma, only the lambda hyperon can be produced in a narrow density region. So the equation of state remains stiff even with inclusion of hyperon. And this is just because of this explicitly dependent hyperon potentials. Okay, just skip this figure. So that means if you have if you can keep the stiffness of the equation of state even with inclusion of hyperons, so that means that the mass remains above these two solar masses, experimental value, and this is a possible way to resolve the hyperon puzzle. Actually, this was a work that we did the last 15 months, because we have a lot of fight to understand these new effects in our calculations. And then we had a big fight with the referees because I don't want to go into details on this, but we succeeded to publish this. Okay, thank you.
Yes. So in this field, the only observables which are available are the radii and the masses of the neutron stars.
Yeah, the mass, yeah. For the radius, so they, at the beginning, they say they had indications that the radius should be low. Actually, this figure which I skipped here. So just look only the solid curves. These are the last calculations that we have. One is without, the other is with hyperons. You don't see any difference in the mass, so the mass remains above the observation. The radius is still big. They had some observations that the radius will be lower. Now there are again other observations that the radius will be exactly where we are. So this 13.5. But it's still an open question, I mean, the radius.
But my question is this, because, I mean, there are only practically two
more.
And what about gravitational waves? I know that...
yes, there are more observables. Moustakidis will say more about this. Concerning this model, we are close to this new experimental data coming from gravitational waves. Okay, not in sight, but very, very close. So it looks very, very promising.
So, good morning. The title of my talk is Neural Networks for Evaluating Induced Fission Product Yields. Now, this is a topic that we have started over a year ago, working at the physics department of the University of Thessaly with my student Vasilis Tsoulos, and part of the calculations were also in his bachelor diploma thesis. Now, nuclear fission, the process where we have an atomic nucleus to split into lighter elements, resulting in the release of a large amount of energy, was first discovered on December 1938 by Hahn and Strassmann, and was explained theoretically in January 1939. But however, although it was discovered 80 years ago, it's still one of the most challenging problems in low energy nuclear physics. So why is this? Nuclear fission is an extremely intricate, non-equilibrium, time-dependent quantum many-body dynamic problem. And its complexities arise from the pivotal roles that are played by various properties of nuclear matter and nuclear dynamics and their interplay at different stages of the process. So investigating the mechanism of nuclear fission is beneficial for advancing various sectors of nuclear physics, going from nuclear structure to reactions and nuclear astrophysics and to nuclear technology. In heavy elements, fission, like actinides or transactinides, fission is a fundamental process that can be either spontaneous or neutron-induced, and its relevance extends from the very existence of super-heavy elements to the reactor neutrino behavior and to the R-process nucleosynthesis in neutron star mergers. Now, in practical applications, nuclear fission data are indispensable, especially for energy production, radiation shielding, waste management, and isotope generation, among other things. So in a broad context, nuclear fission serves as a diverse laboratory to a wide range of scientific phenomena, going from nuclear properties to quantum mechanics and statistical physics. However, the complexity of nuclear fission poses challenges both in obtaining detailed experimental data and also developing theoretical models that can give effective predictions. Experimentally, there is limited access to crucial observables such as the proton and neutron content and the total kinetic energy of fission fragments. And we see that the major nuclear data libraries provide fission yields almost predominantly at thermal neutron energies or at 0.5 MeV, and to a lesser extent for neutrons at 14 MeVs. So the sparsity of data necessitates novel methods in order to account for errors and uncertainties. Now, theoretically, given the limitations, given the intricacies of the quantum many-body problem and the complexities that are inherent in the nuclear force interactions, achieving a deep understanding and detailed simulations of nuclear fission is one of the most daunting challenges in nuclear physics. So nuclear fission, spontaneous or neutron-induced, is beyond the reach of ab initio methods. There are several microscopic models and also phenomenological ones that have been used in order to attain fission yields, but these, the predictive capability of these models is insufficient, especially when we go to cases that we have a few experimental data. So over the past decades, there are two fundamental microscopic properties, frameworks, that have been used in order to simulate the collective time-dependent phenomena. The first one is the time-dependent density functional theory. So given an energy density functional and a pair interaction, they can simulate any a wide range of phenomena. And then it's the time-dependent generator coordinate method, in which the nuclear wave function is expressed as a superposition of many-body generator states that are linked to collective coordinates. Now, when we apply those models, although we get promising results, when we try to do more detailed comparison, they encounter challenges in accurately reproducing the observed data. In addition to that, these models take extensive computational times that can be extended to weeks, even on advanced parallel computing systems. This means that their expansions are prohibitive because they will lead to even further prolonged modeling times, contributing to increased energy consumption and to higher economic and environmental costs. At the same time, the field of machine learning has seen remarkable developments over the past decades and has made a great impact in fundamental research and real-world applications. So recently, the nuclear physics community has turned to the use of these machine learning algorithms that can learn from the existing data and make predictions. So this integration of machine learning with nuclear physics promises to overcome the limitations of the current computation methods and lead to new avenues of discovery and application. And it is in this context that the integration of nuclear fission with machine learning algorithms seems to be a viable solution to the current limitations of theoretical models. So what we have done in this work, we have used as our database to be 48 cases of induced fission mass yields. So we make a deep probabilistic neural network in order to train it and then make predictions for the mass yields of fission of actinides and transactinides. So the database is 48 induced fission mass yields from the GNDL library, and then from that we extracted samples using a machine learning algorithm. This is the Gaussian process regression one, and please check the poster of Vasilis, is poster number 4. There are more details on the method in his poster, and we extracted 470,000 data points, and those served as our training set. And then the experimental set were the 5,000 data points that we get from the GNDL library. Now, the training set with the test set will enter this mixture density network, and after the validation process is complete, we get the predictions for the fission mass yield distributions. So in general, a neural network attempts to approximate a nonlinear mapping using large-scale data-driven optimizations over hundreds or thousands or millions of parameters. So a network consists of layers of a number of neurons. So the first layer is the input layer, and there is where the information enters the network. In our case, the inputs are the atomic and neutron numbers of the fissioning nuclei, the mass numbers of the fragments, and the excitation energy of the compound nuclei. Then we have the output layer, the last layer, that is the output layer. There the results come out from the network. And in our case, this is a mixture density layer, which means that we approximate the distribution of the yields as a sum of Gaussians, and we get back the parameters of these Gaussians. Now, the information travels from the input layer to the output layer through a number of intermediate layers that are called the hidden layers, and each one of those makes different transformation to its inputs. And when the network has more than 2 layers, then it's called a deep network. Now, each neuron in the network receives an information from the connected neurons of the previous layer that can be either the input or some other hidden layer. And after it processes it, it sends a signal or information to other connected neurons. Now, the strength of the signal at each connection is determined by weight, and the weights are the ones that are being trained during the learning process. And then the output of each neuron is calculated, by a function that is nonlinear of its sums of its inputs. So this function is called the activation function of the layer. And then typically a network is trained using an empirical risk minimization. This means that at each point when the parameters of the network are trained in such a way that they are optimized when the difference between the predicted values and the given values of the data set is minimized. Okay. So the first thing to test is the learning ability of our network. So here you can see the cases of induced fission of curium-246 and thorium-232. These are cases that were included in a training set, and we can see that the points are, the black points are the GNDL data, and then the blue line are the MDN evaluations. So we can see that the MDN has achieved what we call the generalization. This means that it has the ability to learn the patterns of the training set without doing any overfitting. And then these are the results for the predictive ability of the network. So we used as a test case uranium-235, and we predict with the network the mass yields for uranium-235 at different neutron energies. So these are the cases of thermal neutrons, and then for neutrons at 14 MeVs. And we can see that this network can predict the structure, the peak position, and the energy dependence of the mass yield distributions. There are some small uncertainties that for the thermal neutrons are around the peaks, and for the case of 14 MeV neutrons are around the valley, so around 110 and 130 here. But these are generally small, and they are within this confidence interval. So I should mention here that uranium-235 was not included in the training set. Otherwise, we don't make predictions, right? And now, so these are the evaluated incomplete induced fusion yields. These are for the cases of uranium-235 at 4.49 MeV and 8.9. These energies were not included in the training set, and there are very few experimental data. So we can see that we can reproduce these incomplete mass yields, although these energies are not included in our training set. And this is the evaluated induced fission mass yields for uranium for different energies. The dotted lines here are the data, and then we have different energies that are predicted from the network. So the features of energy-dependent fission yields can be successfully described by this MDN network. And let me summarize. So for the first time, we developed and applied a deep mixture density network in order to predict the independent fission mass yields of uranium-235 at different energies, especially in cases where there are not many experimental data of fission. And we can see that the predictions of the MDN are satisfactory for the distribution positions, the energy dependence, and the structure of these fission mass yields. So this is optimistic in order to use this as a modeling approach for reliable and quantitative nuclear fission data. The outlook is to apply the network also for other fission product yields as charge yields and total kinetic energy distributions, and then use this trained network in order to enhance the predictive power of microscopic nuclear models. So thank you for your attention.
I have the following question. What is the minimization algorithm which is used in this?
So here, yes.
And how many parameters are fitted to the data? Number of parameters.
Okay, you
If
have
you know.
3 parameters. No, yeah, I mean, we were developing it now. So these are very, like we had those results last week. So these are very, very preliminary. Anyway, so the function that we used here, this is called the loss function. So we use the negative log likelihood. In cases that you have distributions, you need that as your penalty function in order to optimize your parameters. And then the parameters that you have here, you mean the parameters that you get back, are the parameters of the Gaussian. So in our network, we have 3 Gaussians, the mixture of 3 Gaussians, and then you get for each of them 3 parameters.
You adjust only 3 parameters for all this data.
Yeah, I mean, the ones that you get back. But inside, you mean the hidden part?
Inside,
Okay.
inside.
No. Inside, you have many parameters, but you have no control. You train them, right?
Somebody who created the algorithm has this control. You don't know because the code is used as final, but there is some function inside. There is some minimization algorithm which minimizes the RMS factors and so on. There is some number of parameters. I just was wondering, is there some idea how many are they? Because these are the parameters which are adjusted to data,
Well,
primarily.
yes, but here your parameters
Yes,
are
I
your
understand.
weights.
I
So in a sense that we have like, in our network, we have like 10 hidden layers. So we have your input, your output. This is how your network is defined. This is why this is a mixture density network. And then you have 10 layers, and each layer has 100 neurons. We have made tests in order to see with the number of neurons or layers if what changes, or in case you have an overfit, you don't want that. So then you have to find the weights for each one of that.
The program does not give information about these intrinsic parameters, as I understood.
You can print them if you want,
No, no,
but
no,
there is no sense
Just
in that.
wanted to know how. Thank you.
Apart from the substantial predictive power of the method, can we actually use this to understand the physics behind the fissioning yields? Can we get perhaps other observables?
Well, okay, since I'm theorist, my principal idea is, because, you know, this is a model, I need microscopic models. Anyways, so my idea, which started like 4 years ago, before I even knew my student, so was, okay, let's use a network. And since those networks are functions, then I can use this function to implement it in my code and make it better. Like the relative, I mean, I'm using density functional, so relativistic density functional. So that was my first idea, because I know that there are some functions that are used in these time-dependent density functional codes, and I have an idea of which function I want to change. So yeah.
So essentially
But then,
complementary.
but then if you want to put some extra information, what you could do, and this is something else that we are now starting to do, is that you can feed your network with the difference between the prediction of your theoretical model and the experimental data. So then you can see where the discrepancies are, and this is how it will help you then put some physics into this model.
Okay, so essentially this will not be autonomous, right? We'll need
Exactly.
We'll need an theoretical
Yes,
model.
yes. These are the first results. So this is the first application.
Thank you.
And after that, there are many more to come. Yeah. Thank you very much, Varya. Thank you.